I'm Cristiano Longarini, third-year PhD student at the University of Milan, and I'm working mainly with Professor Giuseppe Lodato, but also with other collaborators here in this room. And first of all, I would like to thank the organizer for inviting me to talk about my work, and I'm going to talk about what I've been doing during my PhD, so kinematics and dynamics of gravitationally unstable disks with the phantom. So, before starting, just would like to point out what I mean when I talk about self-gravity and gravitational instability in the context of accretion disks. So a disk is self-gravitating when the contribution of the disk's gravitational potential is significant. So when the disk-to-star mass ratio is significant. And the main consequences of self-gravity are a super-Keplerian rotation curve, as Benedetta has shown us yesterday in her talk. And also the self-gravity has consequences on the structure of the disk, so the thickness of the disk is changing with self-gravity. And so gravitational instability is a linear hydrodynamical instability that can arise in self-gravitating systems, and the main consequences are that there is the emergence of a spiral density structure in the both density and velocity field. And this spiral can transport angular momentum throughout the disk or could lead to disk fragmentation. And so, why gravitational instability? So, if Benedetta and Sal haven't convinced you yet, I'm trying to do it. So, GI is important because if we consider young stellar object in an evolutionary scenario, we have three classes of young stellar objects. So, class 0, class 1, and class 2. And class 0 objects are newborn protostars still embedded into the molecular cloud. And from the spectral energy distribution, we have hints of the existence of a disk inside. Class 1 objects are systems where it is clear the presence of an accretion disk, but the system is still embedded into the cloud, so there are interactions between cloud and disk. And finally, class 2 disks are basically D-sharp disks, so disks without cloud contamination, and where we can observe very well the structure from dust continuum emission. And of course, the disk mass is a decreasing function of the age of the system, so we expect that the system in class 0 are more massive compared to system in class 2. And this can be observationally seen if we look at this cumulative mass, disk mass function in different star-forming regions. So if we consider evolved star-forming regions such as Upper SCO, Chameleon, Taurus, or Lupus, we see that the cumulative dust mass fraction is shifted towards a lower value of dust mass. But when we look at young star-forming regions such as Orion, you see that these functions are shifted towards high dust mass. And so for young systems, the disk mass is higher, and so self-gravity and gravitational instability could be important. And here I'm just showing you two examples where we see gravitational instability acting. So the first one is a class 1 disk, where we see a fragmentation of the disk due to gravitational instability. And this other system, Elias 227, is a class 2 disk, and we believe that it is gravitationally unstable. And so we can see that the gravitational instability is important, of course, in class 0 and class 1, but also in class 2 objects. So if we want to summarize gravitational instability in one slide, we should study these equations. So this is the dispersion relation for a one fluid component thin disk. So the Doppler shifted perturbation frequency is given by the competition of three effects. The first one is the effect of the pressures of the sound speed, that is a stabilizing term. Then we have the second term that is linked to the surface density of the disk, so it is destabilizing since it is related to the self-gravity. And the third one is the epicyclic frequency, so the rotational support of the disk. And if we study the stability, we can define this parameter, the Tumri parameter, that basically is the ratio between stabilizing and destabilizing terms. And the instability threshold is given by Q equal 1. So when Q is higher than 1, the system is stable, while when Q is lower than 1, the system is unstable. And so this was linear theory, but if we want to go beyond linear theory, we can perform numerical simulations in order to study the outcome of gravitational instability. So if we suppose to have a gravitationally stable disk with a Tumri parameter higher than 1, And then we try to trigger gravitational instability or with cooling the disk or adding mass. I will focus my attention on the first one, so by cooling the disk. The Tumri parameter is going to decrease, and eventually it reaches Q equal 1. That is the moment when gravitational instability starts acting. And so there are two possible outcomes of this. So the first one is that there is a thermal saturation regime. So the spiral structure that is created is hitting the disk because of the shocks due to the interaction between the spiral and the disk. And this heating is perfectly balancing the cooling. And so this is a stationary outcome. And the consequence is that there is an efficient angular momentum transport throughout the disk. And basically, this can be seen like a negative feedback of the system. So the system response to the instability is to saturate it. And the second outcome is fragmentation, and it occurs when the spiral structure is not able to balance the cooling. And the consequence is an exponential growth of the perturbation, and eventually the disk will fragment. And this can be seen also with like a positive feedback. And the threshold between saturation and fragmentation is going to be discussed here in the next slide. So when we want to study with numerical simulations gravitationally unstable disk, there are two important parameters. The first one is the beta cooling. So it is the rate with which we are cooling the disk. So in numerical simulation, what we do is to simplify a lot the way we cool the disk. So basically, we define this dimensionless parameter, beta cooling, that is the ratio between the cooling time and the dynamical time of the system. And what we do is to define a threshold, so a critical value. When the beta cooling is higher to this critical compared to the critical value, it means that the cooling is slow, and so the system is not fragmenting, and it is in a thermal saturation regime, the one I was discussing before. And in this regime, the delta sigma over sigma, so the amplitude of the spiral, is directly related to beta with this relationship. And what is also important here is that within this beta cooling prescription, in thermal saturation regime, the amount of angular momentum transport throughout the disk by GI is completely given by the cooling, with this expression where alpha GI is the Shakura-Soniaev alpha coefficient, and it has been also verified by numerical simulations by Lodato in 2008. And so the second outcome is fragmentation. So when the cooling is fast enough, so when it is smaller than the critical value, the system is fragmenting. And what is the value of this critical parameter of the critical beta cooling? I mean, it's a matter of debate, but here I tried to summarize a bit what has been done in the past years. So firstly, Gemi in 2001 studied this problem with the two-dimensional local simulations. And he found that the critical value is about 3. Then Rice et al. In 2005 performed three-dimensional SPH simulations, and they found that the critical value should be around 6. But then, I mean, a lot of other studies have been done, like the one from Merriam Bate in 2012, and they found that the critical value should be higher than 15, but they did not find convergence between 3D SPH codes and 2D grid codes. And I think that the last work here has been done in 2018 by Deng, and they found that the critical value is 3, so like the first one, and they found convergence between 3D SPH codes and grid codes. And the second important parameter when we perform numerical simulations is the disk to star mass ratio, and it determines the morphology of the spiral. So the disk to star mass ratio is related to the winding angle and the azimuthal wave number of the spiral. And in particular, massive disks show fewer spiral arms and more open spirals. And so the relationship I've explained to you before can be obtained by simulations. So this is how the amplitude of spiral perturbation scales with the cooling factor. And we see that the relationship we expect is retrieved for different disk to star mass ratio. And also, we can also study how the spiral morphology is a function of the disk to star mass ratio. So here in this bottom row, I'm plotting the power spectrum of this spiral. So the peak of the power spectrum is the dominant mode here. And you can see that by increasing the disk to star mass ratio, the dominant mode is lower. So we have a lower number of spiral arms, and it is, I mean, I did this for 3 different values of beta cooling. It is respected. So now I would like to talk about the first topic of this of my PhD, that is gas kinematics in gravitationally unstable disks. So gas kinematics is a hot topic now in protoplanetary disk community, and thanks to MAPS and ExoALMA large program, we are pushing ALMA spectral resolution towards incredible limits, and we are actually able to measure very small deviation from Keplerian rotation in protoplanetary disks. And what we measure with ALMA is the Doppler shift of molecular line emissions, and we can, in protoplanetary disk, there are a lot of molecules we can use for this, like CO isotopologs, but many others. And what we are measuring is the local gas velocity inside the disk. And of course, because of projection effects, what we measure is a combination of the radial, the azimuthal, and the vertical component of this velocity field. But since they are on orthonormal basis, in principle, we can disentangle the 3 elements and like have profiles of the radial, azimuthal, and vertical component alone. And during the last few years, we have been observing a lot of deviations from Keplerian rotation. And these signatures can give us insight about processes happening in the disk. Like here, the interaction between a protoplanet and the accretion disk. But also, what I'm interested in is this last picture that are kinematic signatures of gravitational instability. So Cassandra Hall in 2020 performed phantom simulations of gravitationally unstable disks, and then post-processed them with MC-FOST. And she found that the gravitational instability leaves clear kinematic signatures in molecular line emission. And you can see from these pictures what I'm talking about. And the nature of this perturbation is global rather than localized. And the shape of the perturbation is determined by the spiral and the disk properties. And so what we did in this context was to give an analytical description of this perturbation that is called the GI wiggle. And we performed the first order perturbation of the fluid equation for the system, and we made some hypotheses. So we considered a 2-dimensional system, so a thin disk, that is marginally unstable, so with a Tumri parameter of 1, in thermal saturation regime, so that the density perturbation is given by the cooling factor. And so what we are doing here is fixing the amount of angular momentum that is transported throughout the disk, and also a nearly Keplerian disk. And here we obtained the radial and the azimuthal component of the perturbed velocity field. As you can see, they depend on the cooling factor and on the disk to star mass ratio, basically. And yeah, so if we have the velocity component, we can sketch observed velocity fields. And this is one of it. So here I've plotted this function, so the observed velocity field. And you can see that the perturbation is global, and it is visible in a different channel of this velocity map. And it's particularly interesting if you look at the central channel, this one, that in for Keplerian rotation, we expect it to be a straight line, but here it's showing this oscillation. And I think this is the most important characteristic of this kind of perturbations. And so here I'm just showing you how different channels of this map and how they are perturbed by the presence of the spiral. Yeah. Okay, and here I've subtracted a Keplerian model to the perturbed one in order to see the residuals of this map. And you can see that there is this interlocking finger pattern, and this lack of speed and excess of speed parts of the map are matching the position of the spiral. And it is something that has already been pointed out by Cassandra in her work in 2020. So she is finding the same we are describing with the analytical theory, and it's very nice. And so, I mean, we have this perturbation, the GI wiggle, and we want to understand how it depends on different parameters of the disk. So The amplitude of the perturbation is, depends on the cooling factor, so on the amount of angular momentum we are transferring in the disk. And also, it depends on the disk mass, so it increases with the disk mass. And you can see that there is a degeneracy between these two parameters in terms of amplitude. While the frequency of, this perturbation increases with the azimuthal wave number, so with the number of spiral arms, and decreases with the opening angle. And as I was saying before, there is a degeneracy between the disk mass and the cooling, so the angular momentum transfer throughout the disk. And if we want to obtain information about this second quantity, so the cooling time, we need to break this degeneracy. And since we are dealing with massive disks, we can use the rotation curve method explained by Benedetta yesterday to obtain a disk mass estimate and then break the degeneracy and obtaining the cooling factor. And when we fix the disk mass, the amplitude of the wiggle scales as beta to the power minus 1.5, as expected from the linear theory. And so if we know the disk mass and we observe a GI wiggle, we can, in principle, constrain the cooling factor. But before doing that, we want to be sure that our linear theory is valid. And so we compared the theory with numerical simulations. So in this work, Jason Terry, in 2021, studied how the amplitude of the GI wiggle changes as a function of the disk mass. And we found that it is well described by the theory I've explained to you so far. And also the relationship between the frequency of the perturbation and the number of spiral arms and the pitch angle is retrieved as expected from the linear theory. And here in my work, I've also tried to apply the method I've explained to you before to obtain the cooling factor. So I took a GI simulation. I computed the disk mass from the rotation curve. And then I measured the wiggle. This is just from the hydrodynamical simulation, so no radiative transport effects. And so I computed the amplitude of the perturbation, and I tried to constrain the cooling. So the input parameter was beta equal 8, and I obtained beta equal 9, so that, I mean, it's quite good. But what we found is that, the shape of the wiggle is well retrieved in this case. But if we turn the spiral, it's a bit trickier because we need to pay attention on how the spiral is oriented. And sometimes the dissipations due to the viscosity in the simulations are canceling the signal, and because the viscosity is not taken into account in our model. So now we want to apply this method to an actual system, so to Elias 227. It is a self-gravitating disk, as Benedetta showed us. So the disk mass is a considerable fraction of the stellar mass, and we expect that self-gravitating effects are at play in this system. And it also shows global deviation from Keplerian rotation in the observed velocity field. As you can see here, there are a lot of these perturbations. And so what we tried to do is to, by knowing the disk mass, to constrain the cooling factor, or equivalently the alpha viscosity, through the amplitude of the wiggle. And this is what we obtained. So a cooling factor of 10.5 or alpha GI of 0.038. And this is just a comparison between the shape of the central channel in the model, so the black line, and what we observe, the blue line. Of course, I mean, the morphology is not the same. What is the same is the amplitude of the perturbation. That is what we are trying to constrain here. And so we have a measurement of alpha viscosity in this system. And so we suppose that the system behaves like a self-similar. And we can obtain the accretion rate onto the central object from the theory. And so we put this value inside the equation. And so we have a theoretical estimate of the accretion rate onto the central object for this system. And so the measured accretion rate is 10 to the minus 7.2. And the one we are predicting with gravitoturbulence is 10 to the minus 6.9. So it's quite close, and it is within the error bar. So we are, I mean, this can be another signatures that this system is gravitationally unstable. And yeah, so now I would like to talk about the second part of this of my PhD, that is the dust dynamics in GI disks. And I think that this work is really complementary to Saul's one. And I would like to thank him for feedbacks and discussion we have had during the last few months, because I think it improved a lot my work. And so what we know so far about dust dynamics in GI disks. So from SPH simulations by Rice, they found that spiral arms are efficiently trapping dust because spiral arms are both pressure maxima and gravitational potential minima. And so the dust trapping is really efficient, and the dust-to-gas ratio inside this structure can reach also values of about 1. And sometimes the dust is so unstable inside this structure that can collapse, forming clumps of one Earth masses. And Rice proposed this as a way to form planetesimals or planetary cores in early protoplanetary disks. But this is just a warning, so these were low-resolution simulations, and they were not able to properly resolve dust clumps. And another important work in this context is Booth and Clark 2016. So they performed two-dimensional SPH simulations of gravitationally unstable disks, and they studied dust dynamics. And in particular, they focused their attention on the dust dispersion velocity, so the level of excitation of dust inside the simulations. And they found this scaling, so the dust dispersion velocity is proportional to the Stokes number to the power minus 1.5 and the cooling factor. And where the Stokes number is just a dimensionless measurement of the aerodynamical coupling between gas and dust in these structures. And then, recently this year, I have worked on an analytical theory, let's say, about dust in gravitationally unstable disk. I won't focus talk on this, but if you're interested, we can speak about it. And basically what we have found is that the presence of dust is making the system more unstable. And if dust is sufficiently cold and sufficiently abundant, it can drive a gravitational instability but a small wavelengths. And it could explain the formation of gravitationally bounded objects of about Earth masses. And so what we are doing now with Phantom are two things. So we are performing simulation of gas and dust gravitationally unstable disk with two fluid implementation. We want to compare to the linear theory I have done this year. And also we want to study the parameter space better than in the previous simulations. And now I'm focusing my attention on this second thing, so the study of the parameter space. So we want to understand what happens to dust in GI disks. So why dust is excited in these disks. So if we imagine a dust grain and a gas spiral arm, when the spiral arm reaches the dust grain, it kicks it, and this kick is exciting dust particles. So dust particles can be efficiently excited or not efficiently, and it depends on the spiral parameters. So the dust is efficiently excited, so it receives a strong kick if the cooling time is low, so if the strength of the spiral perturbation is high. And then if the disk to star mass ratio is high, because if it is, this is low disk to star mass ratio, sorry. So if the disk to star mass ratio is low, we have a number of spiral arm that is bigger, and so the dust is receiving more kicks. And finally, if the Stokes number is high, the dust is not so coupled with the gas, and so the drag force is not damping the kick, and so it is efficiently excited. While the dust receives a weaker kick for high beta, so if the strength of the spiral perturbation is low, for high disk to star mass ratio. So because for high disk to star mass ratio, we have smaller number of spiral arms, and so the dust is receiving less kicks. And for low Stokes number, because the drag force is damping the spiral kick, and so it is less excited for this reason. And so what we are doing with Phantom is to perform simulations, numerical simulations with the two fluid implementations with a high resolution. And we are studying both gas, large dust grains, and small dust grains. So we try to explore as much as possible the parameter space, and this is the set of simulations I've performed. So 3 different distance mass ratio, 5%, 10%, and 20%. 3 different, yeah? Okay, I'm pretty done. 3 different beta cooling, so 8, 10, and 15, and 2 different dust sizes that corresponds to an average Stokes number of 40 and of 8. And so the question is how the GI parameters, so the cooling and the distance mass ratio, are related to the dust parameters, so the dust to gas ratio and the dispersion velocity of the dust. So here just to show you some histograms I've done. So what we found is what we expected. So for high distance to mass ratio, we have less spiral arms, and so the dust is less excited. For a high beta factor, the spiral arm is weaker, and so the dust is less excited. And the aerodynamical coupling is damping the spiral kick, and so for high Stokes number, dust particles are excited more effectively. And this is the scaling Booth and Clark found, and this is what we are finding in our simulation. So I say that it's a pretty good agreement, and the different shapes are different resolution simulations. And finally, just to talk about dust collapse. So we observe in a subset of our simulation dust collapse, and it is exactly south simulation's range, so it's reassuring this. And we observe dust collapse only for high distance to mass ratio, long cooling time, and small dust particles, as we expect, because these are the 3 most unstable configurations. And this is an example of a simulation where we found dust collapse, and we find a mass clump of 0.8 Earth masses. So we are able to resolve it, and we have also verified that the smoothing length of the gas is smaller compared to the one of the dust, in order to be sure that it is physical collapse and not artificial. And here in this plot, I am showing the average density of gas and small dust particles, and you can see that the collapse is happening only on dust particles. But eventually, when collapse happens, the simulation stops because of the too long computational time. And the problem is that the stopping time is inversely proportional to the dust density. So if it goes to infinity, this goes to 0. And the problem is that the stopping time is smaller than the time step of the simulation. And so that's why I'm interested in implementing dust particle sink creation in Phantom. And yeah, here I can leave you with my conclusions. But I think that the most important thing for me is that hydrodynamical simulation can allow us to test the theory and to understand the limits of the theory and also the applicability. And I think that Phantom is doing a really great job in this context. So thank you very much for listening.
You said that you developed also an analytical theory for this phenomena. Did you find agreement with the mass of the clouds that are forming?
Yes. So from the analytical theory...
Nothing that you consider also analytical?
Yes, so with the analytical theory, we can obtain an estimate of the Jeans mass of the perturbation. And what we found is a pretty good agreement. So for this case, that from the simulation, we obtained 0.8 Earth masses. The expected one was about 2 Earth masses. So, I mean, pretty good agreement for this.
I was wondering about your comment and maybe Joe's comment as well. So this issue when the dust collapses. Yeah. So I understand why it is physically correct and why it's weird. Because it's basically like the drag is proportional to the, it's the surface area of the grains, but then the number density of grains also matters. It's how many grains per unit volume you have. So you get a very strong drag whenever the dust density gets very high, because anything dragging through that will see a lot of dust. So so it's physically correct, but it's weird that you could have dust like collapsing, but then somehow like getting perfectly stuck to the gas. So I don't know what the right thing to do is here physically.
Yeah, so physically, the nature of the collapse is just gravity. So,
right, but it's also true that if you collect dust in a very concentrated lump in a bunch of gas, it should have a very strong drag because a lot of grains, like basically feeling getting a high surface area.
So what I expect from this plot, if I could continue the simulation, is that maybe also the gas is...
Yeah, maybe that's the answer. Maybe just physically it should just drag the gas with it.
Yeah, but I'm not sure that as well, so it's...
So so if that is true, then an implicit scheme would be the answer, because then you say, well, it should drag the gas down with it, and you would drag the gas down onto your Earth mass core, maybe make Jupiter immediately.
Yeah, because by adding a sync particle, we are just avoiding the problem. Yeah.
Right. I wonder if Joe if you have an answer.
I don't have an answer to that, but I know chemical engineers have dust going through gas, and it can be unstable. The dust just, it's actually a Bernoulli instability. Hello. It's a Bernoulli instability.
Okay.
So there are instabilities which come from dust moving through gas, but that doesn't answer Daniel's question.
Actually, maybe the missing physics is actually growth.
Yeah.
Because the thing that's wrong is that the dust grain size is like staying the same, right, during this collapse. So whereas if you concentrate dust a lot, what would happen is, you want to grow it into an Earth, right? But and if you pile a whole lot of dust in a small volume, the thing that's not changing here is the dust grain size.
Exactly, it is fixed. Yeah, because if it is growing, also the aerodynamical coupling is weaker because dust particles are bigger, and so maybe this could solve the problem actually. Yeah. Yes.
In one of your early slides, you showed some calculations for, thank you, for beta. It's probably your second slide, I think. Matthew Bate and somebody else did a calculation and got a number, and then somebody did a 3D calculation with a finite difference scheme.
This one?
Yes, Maru and Bate, 15. And Deng et al., they get 3. What is the difference between the systems in Maru and Bate and Deng?
So I'm not so sure about this. Yeah. So here they focus their attention on the role of the shock capturing viscosity that can change the critical value of beta because of the balancing between heating and cooling. And so here they found that the value of alpha and beta viscosity can change the critical value of the beta cooling.
Well, it's not only the critical value, you've got a phrase there, non-convergence.
Yeah, they did not find the convergence between 3D SPH and 2D grid. I'm not sure, I'm not an expert of these two papers, so I'm not sure.
Got convergence.
Yeah. I need to, look better at this paper. So I've just taken the results, sorry.